after he retired.
Good. Well, thank you so much for coming out this morning for this program. My name is Karen Tucker, and I'm CEO of the Churchill Club. Our discussion this morning is about machine learning, what's happening, what it means for future innovation, economic growth, competitiveness, etc. We have a terrific group of speakers here to lend their opinions about that as well as their insights. We have Jeremy Howard from Kaggle, Peter Norvig from Google, Gurjeet Singh from Ayasdi, and they will be led in conversation by Janet George from Accenture. Thank you all so much for being here this morning. Thank you also to Accenture for graciously opening your doors to us this morning and for your partnership in this program. We really appreciate that very much. A brief introduction to the Churchill Club. We are Silicon Valley's premier independent business and technology forum. We've been convening unique Silicon Valley style conversations since 1985. Recall Windows 1.0 was just coming on the scene at that time, so quite a bit has happened in those intervening years. What drives us every day is to encourage innovation, economic growth, and social good. And we do this through the up to 40 programs that we present each year, where like minds can connect with ideas and with one another. We are a member-supported organization, so if you have an interest in that, we would encourage you to check it out. Next up, we present EMC President and COO David Goulden on August 8th in conversation with Mark Garrett, who's EVP and CFO of Adobe. And Goulden is said to be the odds-on favorite to assume the CEO position when that becomes available at EMC. Let's see what happens. Next, we'll look at growing companies over economic changes and leadership changes as well. And we have NetApp CEO Tom Georgens, SVB CEO Greg Becker, and Yahoo Acting Chair, as well as LiveOps Chair Maynard Webb. They will be led in conversation by Rich Karlgaard. Finally, on September 26th, one of our most exciting two events of the year, we have our annual innovation day-long conference called Changing the Game. This year's theme is power and the changing constructs of power that we are experiencing in our lives today, from being enabled by mobile and digital technologies to changing views around collaboration and leadership. That same evening, we present the Churchills, which is a program to inspire us by highlighting excellence in 4 things we care about: innovation, collaboration, leadership, and societal benefit. So hope you can join us for those. We're very excited. If you're tweeting, please use the hashtag Churchill Club, and you will find other Twitter codes in your printed programs. Our moderator, Janet George, is Managing Director at Accenture's Technology Labs. She leads the Cognitive Computing Team, which is a group that thinks deeply about topics such as deep machine learning, big data, and much, much more. She's especially interested in exponential growth opportunities and next-generation technologies that span industries. Her background is diverse. Having worked at HP Labs, Apple, Yahoo, and eBay, we definitely look forward to the conversation that Janet will lead for us this morning. Please give your warmest welcome to Janet George.
Welcome. Can you hear me? Okay. So, one data point. Steve Ballmer was part of Churchill Club events. And when he was asked about big data, he said it's a machine learning problem. So today we have 3 very remarkable people on this panel. And they are uniquely qualified to have this discussion around machine learning. So we're going to get started. Briefly introduce yourself, and then we'll jump into questions.
Hi, I'm Jeremy Howard. I'm the President and Chief Scientist of Kaggle.
Peter Norvig, Director of Research at Google.
Gurjeet Singh. I'm a co-founder and CEO of Ayasdi.
Great. So I'm going to ask each of you some questions, and then we'll go around. First to you, Jeremy. Machine learning has been around for a very long time. So we are very interested in knowing what's hot. Why is this suddenly hot? So tell us about some hot trends in the machine learning space.
Sure. So machine learning really appeared in the 1950s. A researcher at that time was trying to develop a computer program to play checkers, and they realized that they didn't know enough about checkers to program good rules to play checkers, so they did something really interesting, which was to set up some broad parameters around how one would play checkers, and then get the computer to play against itself. And as a result, he was actually found himself with a program that could beat him at checkers. So it goes back, as you said, a very long way. I've been personally involved in machine learning for 20 years. Back then I was doing neural networks in large banks, particularly for things like marketing and credit scoring and fraud. In a lot of ways, things haven't changed a whole heap. I mean, back then we were working on large data sets, and we were, identifying people who might churn or people who might cross-sell and so forth, and they're some of the same conversations I'm having today. The difference was at that stage in Australia, maybe there was 3 or 4 people working in the field, and there was maybe 4 or 5 companies with amount of data and money to invest. Today, every company, if they're not working with machine learning, is probably shortly to go out of business, because the folks that are leveraging this technology, like Google most particularly, are powering ahead. The really big trends today is that there are now 2 classes of machine learning technologies which require much less hand-holding and kind of specific expertise, one being ensembles of decision trees, the other being deep neural networks, which can handle nearly any problem, everything from image recognition to speech recognition to automatic drug discovery. And those are the 2 fields which are really making a big change right now.
Excellent. So I think for the audience, you might be familiar with shallow and deep learning. We'll talk a little bit more about deep learning. Deep learning has gained a lot of attention in the last couple of years.
Yes, it has.
Peter, one of the trends I hear a lot about is machine learning is everywhere. And we know machine learning is everywhere in Google. It's almost in the DNA for Google. So tell us a little bit about what you see is hot and new, and also what are some of the lessons you're learning, because you're far ahead of the game compared to the rest.
I guess for us what's new is looking at new sources of information. So we started off saying our domain is the web and the text on the web, and there's techniques for dealing with text. And now we're in, there's so many sources of information. So we're dealing with images and video now. We're dealing with maps. We're dealing with links between people, relationships of who's sending email to whom, who's sending messages of various kinds, and what does that tell us about it. And then we're also trying to do more with what we have. So you started out, the type of text processing we would do is say, well, what are similar words? If a person types a couple words into the search box, what are synonyms or near words to that we should kind of add into the query to help them find something even if he didn't know the exact right words. Now we're doing things more like, if you ask a question, do we know a fact? And some of these facts we can find in places like Wikipedia and build a big database of them and retrieve them when we think you're asking about them. Others we find on web pages and we piece together. And we find them in tables on web pages. We say, let's parse a web page. It looks like this is a column header and this is a row, and the entry here is a fact. Let's store that away. And we find it in text. Here's a sentence that says this company was acquired by this company on this date for this amount of money. Let's store that away as a fact. So more types of information, trying to integrate them all together. And now we have the problem of what happens when you have conflicts. And there's been 2 approaches to that. One is to up front say we're only going to accept stuff that we know is true, and so have sort of a guardian entry into the database saying we're only going to allow well-curated information in, and now the retrieval process will be easy. Some people have taken that approach. Wolfram Alpha is a good example of a question answering system that takes that approach. We've taken the approach that we're going to let everything in and then we're going to sort it out afterwards. So we have to have techniques to say not only can we retrieve, which is what we did in the past, but also can we evaluate to say, here's a conflict, what's true, what can you trust, and what do you not trust? I think that's where a lot of the action is now.
Yeah, and the Q&A system is very interesting because, as some of you know, Watson had built the entire system based on Q&A and hypothesis. And the problems we see with the Q&A system is you're forced to give a single answer. And usually there's multiple answers to a question. So it's very gray, and you can't just expect one answer. It's better if you go with a search assist type model where you're assisting the customer to pick one of the many models. Okay, so for Ayasdi, I think it's a great model, you know, the whole query-free searching and discovery. So Ayasdi, I'm very impressed with just the approach. Can you talk a little bit about the approach and this changing, igniting new ways of doing things?
Right, absolutely. So, you know, our background is we started out from Stanford many years ago, and the challenge was that DARPA and NSF saw a change in the way people were doing science. They saw a change in which people started doing science by creating new large complex data sets. And they figured that people who were making the best complex data sets were probably not the best people to analyze them. So they had this problem that they are investing hundreds of millions of dollars every year in the creation of data and next to nothing in understanding of data. So their challenge to us way back when was how could you sort of build systems that will automatically build and evaluate models on large complex data. And at Stanford, that's what we attempted to do. We basically used this very old branch of mathematics called topology, and we said we want to be able to build different machine learning models about data, and then we want to be able to compare them. And that turns out it's not an easy problem. We worked on it for quite a while, and that's what we do at our company now. You know, our fundamental idea is that every company in the world needs more data scientists, and there aren't enough of them. So there are a few ways to go about it. You can either hire people somehow, external people to be data scientists for you. You can make your internal data scientists much more effective at their job. Or you can convert masses of people who are not data scientists but know something about data into data scientists. And that's what we are about. We are about basically empowering people to be able to do more because our platform in its automated way will actually do quite a bit of what people would manually have done otherwise. So that's sort of our approach to the problem, is instead of sort of manually writing code and manually writing queries, to essentially use computation. If computation gets cheaper over time, we'll be able to do more.
So how do you see the adoption curve? Because we've lived in a world of databases forever.
Absolutely.
We've lived in a query world, right?
Yeah.
How do we emerge out of this database world and the query world?
You know, it's very interesting because we see it's a very polar world, right? So when we go talk to our customers or in general to executives, we either get thrown out of offices, that happens quite a bit, or it's the case that people understand that the onus of coming up with hypotheses from data should not rely solely on human beings, right? That machines should be able to come up with hypotheses around data, at least statistical facts about data. And the adoption curve, you know, it's very interesting for a company like us. We are just getting started. We are only about 60 people. It's a good thing if there's a small set of people who love you, right? We don't need the whole world to love us right now. Eventually they will, so we'll get there. But it's very interesting. You know, we have more than enough demand in the market right now that we are very happy with the growth that we are seeing.
It's a different mindset to be able to say, I'm going to discover something from my data.
Absolutely.
I'm not going to come out and start asking a lot of questions of my data, which is your traditional query model.
Absolutely.
Jeremy, for you, enterprises is an interesting, you know, their cycles are very long. They have proprietary data. How do you see the adoption happening with machine learning within enterprises?
There are certain leaders in that space. I guess our client GE would be probably the leader of those leaders. They've invested very heavily. They are building a very large team in San Ramon. And really, Jeff Immelt, the CEO there, has really recognized that a company like that either learns to leverage these technologies or they get out-innovated by the new players that they haven't even come across yet. If you're Kodak, it's too late by the time you realize that a company with 11 people has just eaten your lunch and you're out of business. So, there are some...
There's a question whether Kodak really knew what business it was in. Was it in the business of making memories, or was it in the business of making,
There's certainly that, but there's also just a case of understanding what modern technology can do to transform your business. And in the area of data, there is no business so we have a community of over 100,000 data scientists. We've worked in every industry, and I've never come across an enterprise who, when I said to them, my first question is generally, tell me your top 5 strategic priorities in your business corporate-wide. And generally, at least 3 to 4 of them are things where a data-driven approach could be totally transformational. The big challenge is cultural. Yes. People get to the top of enterprises because they're domain experts, and they've been domain experts for decades. And by the time they get there, they've surrounded themselves with other domain experts who they trust. So to be able to say, okay, we're investing in machine learning, we now have approaches to data-driven decision-making, that's tough. Even tougher is we're going to transform the organizational culture so that we trust those data-driven decisions ahead of our industry expertise. And I think that's the thing that's going to separate, companies like GE, where they have driven from the top, this is what we're doing, from companies where the senior executive team is not, equally passionate about taking to this approach.
I want to talk a little bit about Google Brain, because I think it's fascinating that Google can come up with, mimic the neural network basically, and then here's Google Brain, right? Amazing, deep machine learning, unsupervised. So tell us a little bit more about the background and how you see it going, where you see it going.
Okay, so the background is goes long before Google, and it's called Google Brain. I think of it more as mathematics than as neurology, but there's 2 metaphors that drive it. And the idea is to do machine learning in a way that builds up intermediate representations. So machine learning is mapping from inputs to outputs. If in high school you drew these XY plots and here's some data points, and you drew a straight line between them, or you drew a parabola between them and tried to find the best one, that's all machine learning is. So the majority of machine learning is just an elaboration on that, drawing that curve. You have the X inputs, you have the Y outputs, what's the best prediction? Now what deep learning says is we're not going to do this shallow prediction directly from a X point to a Y point. Rather, we're going to make up some stuff in between. So we're going to try to learn this black box that takes inputs, goes through various steps, and then comes out with outputs. And we're going to do that not with the direct mapping, because that's going to be really hard to do, but we're going to do it by inventing the intermediate pieces. And this has been a goal for decades in machine learning. Really started to come into play in 1996 when a group at Berkeley that combined computer scientists and neurologists that were studying the visual cortex said, we're going to do image recognition to go from some pixels to say that's a dog or a cat or whatever. And we're going to do that by building up the intermediate steps, by saying what are the components of a picture. Rather than just going directly from pixels to dog, we'll go from pixels to some little line segments, to the line segments coming together into some bigger thing. So instead of having one function, we're coming up with multiple functions, but the hard part is we don't know what the inputs are for the intermediate level functions. One way I like to think of it is saying it's this problem of image recognition, but we can think of it as image duplication, to say, can we represent this image that I'm given in a more compact way with a representation in terms of function. And so an analogy I give is, say you were a jigsaw puzzle manufacturer, and you have a bunch of jigsaw puzzles in boxes. And now one of your engineers say, well, let's allow somebody to upload a picture, and we'll make that jigsaw puzzle for them. But your guy in inventory says, well, it's too much trouble to create custom jigsaw puzzle pieces for every puzzle that gets uploaded. So let's just have a set number of pieces, and when somebody puts in an order, we'll pick them out of inventory and put them into a box. And now the question is, what are the right pieces that you need? And you say, well, you know, it'd probably be good to have some eyes, because a lot of pictures have eyes in them, and maybe some noses of various skin colors and so on. Then a lot of blue for the sky in the background and some green for the grass. We don't have to get them exactly right. We just have to get them approximately right. And so what deep learning says is, what's the 1,000 most important puzzle pieces that you could put in inventory so that when anybody uploads a new picture, you can say, I'll pick these out. And you know, as a human, understanding the type of pictures you're likely to get, you come up with ideas like eyes, noses, and so on. And up until 1996, nobody had been able to do that. Nobody got a computer to invent those types of pieces. And then they got it to invent lines. They said, okay, pictures are made out of lines. That's a good step. And people kept on working on it. And then in 2006, Jeff Hinton's group finally came up with eyes and noses. They did this, and they looked at the intermediate level and said, aha, it's invented the notion of an eye and a nose. And then Andrew Ng's team in 2009 did a little bit of advance on that. And now we've got these multiple levels of here's the lines, here's the eyes and noses, here's the faces, and here they are all combined together. We're able to do that just by writing a mathematical formula that says, tell me the best pieces that if you assemble them will give me this picture. So that's worked out. We were able to assemble most of the players that played key parts there at Google, attracting them by saying, well, we got all the data and we got all the computers. And we have some of our top, not data scientists, but computer architecture scientists saying, how can we put this together to build a computer that's going to be more efficient than anything that was done in the past? And so we were able to build models that were about 100 times bigger than had been done in the past and shown great results. So we were able to, there are these standard databases of image recognition tasks, and we were able to cut the error rate in half on that. Speech recognition is another field that has 30-year history. And people are getting to the point where if you make a change and you eke out a 1% improvement, it's high fives all around. That's a big change. We put in the deep learning and we got a 30% improvement. So that was many years of research, probably decades of research, all in one technology. So it's excited the field a lot and is one of the important areas now.
You mentioned you're interested in exponential technologies.
Yes.
And so I teach at Singularity University, and Peter's
Yes.
been involved there as well. And
Yes.
just to kind of say why this is important, like you might be thinking, well, great, they found lines and then they found eyes and noses. It's like, okay, before that, people did by hand have
Yes.
algorithms to find
Yes.
eyes and noses and lines. But
Yes.
the thing about what Peter's just described is it's exponential in nature.
Yeah.
We've got to the point now where the progress I've seen in deep learning in the last year kind of eclipses the previous 30 years. And the next year will eclipse that times 30. Like we're now at the point where it's finding stuff itself.
So you have gained momentum, very significant momentum.
Yeah, and the computer creates its own momentum. So, now the only thing we're doing, with the big issue now is the architecture issue. And so, for example, at Google, they have huge banks and racks of graphics processing units, which can do these things billions at a time. So we've hit the exponential point in deep learning, and that's why everybody's going to see it in the next 2 or 3 years.
Yeah.
And I think there's a lot of room for improvement there in the architecture.
Yeah.
Right, so
Definitely.
we sort of had a race internally between the sort of basic Google architecture that was existing in our data centers and the specialized GPUs. And the Google data center won. I think it wasn't fair. They had Jeff Dean on their side, who was sort of the architect of the whole system. But for us, it's a sort of a way to see into the future in the way that Xerox PARC in the 80s put a $250,000 workstation on every researcher's desk because they knew in a few decades that would be a $1,000 workstation. And so we're doing the same thing by killing this problem with a Google data center, whereas we know at some point it's going to be the specialized GPU hardware that will be much more efficient and lower cost.
There's sort of an interesting point here, which is, it's such an exciting field, but it's really inaccessible to most people outside of places like Google. Actually, maybe there are more places in Silicon Valley in which you have access to these technologies and these resources. But there are two things, right? It needs lots and lots of computation. it required Jeffrey Dean and a bunch of computers at Google to make an advance. It also required the best minds in the world all working together, right? There's Andrew Ng working at Google. There's Jeffrey Hinton now. These are resources that are not ordinarily accessible to most other companies in the world, and that's something that we see even for other machine learning areas, not only for deep learning, that there are technologies which can actually help many companies in the world, but they are just simply not accessible. Most companies in the world are not able to hire the expertise, and they don't have the expertise in the infrastructure itself. And so that's also something that we are trying to bridge somehow. Is that you want to be able to make these things accessible to a wider variety of people.
Well, interestingly, of the three of us, we each have a different and complementary approach. So the work that you and Gunnar did in topology,
Right.
you're making accessible to the world by packaging up into software.
Right.
The accessibility of the world's best brains in data science, we're making available by basically making so anybody can come to our website and talk to them. And then Peter is creating a service that anybody can use. So I think the thing is these technologies, yes, they took an Andrew Ng or a Norvig or a Gurjeet Singh to build them, but they're becoming increasingly accessible to enterprises, individuals, and so forth.
I agree. I think our two companies take a complementary approach to the problem, but we are both sort of our mission is the same, right? To make it accessible to a larger variety of people.
Let's talk about security, because I want to say national security and machine learning, right? This is an interesting area, especially because machine learning has grown so much. What do you guys see the play there? Where are the gaps? What are the implications?
Oh, us? Yes. Oh, okay. Look, security is an area in which you have an adversarial situation, an adversary who's changing on you very, very quickly. And so in the past, most of the systems available in industry for dealing with these problems were sort of rule-based, in that a team of people would spend some time, come up with a bunch of rules, and then every time some event happens, you run through a bunch of rules, and then you basically say, well, most of my rules said maybe don't do this transaction, or maybe this looks fraudulent, I'm not going to do it. And it actually works it works well enough. But it's a case that with technologies getting accessible to your adversaries, now it's a case that GPUs are available to mine bitcoins, and there are things called rainbow tables available for cracking passwords, right? And these are available to your adversaries. And so it's not good enough anymore to just say these are my 50 rules, and I'm going to run everything through these rules, and then we'll see what happens. That you need sort of a constant feedback loop, in that you have a stream of incoming data, you constantly keep rebuilding models, and you constantly keep updating yourself, and you have to sort of be on your toes, otherwise. And I think, Peter, you were saying earlier you had seen this problem at Google with spam and so on. It's a very complementary situation in that sense, that it's not a. So this very quickly changing adversary is a problem that you see in many different areas, and it's a.
So the question is, like, can we take machine learning and make it more dynamic, right? Because
that's the only thing we
signature
can,
is very changing fast.
That's the only thing you can do. There is nothing else to. You can't just make rules by yourself anymore. It's not feasible anymore.
Interestingly, there was actually a revelation came out this morning that some of you may have seen in The Guardian. It's actually the biggest revelation that's come out so far. And it turns out to be exactly at this intersection, just as you're describing. And it basically turns out that the NSA now has machine learning algorithms that they can apply to the feed that comes straight off the cables. And they're actually not quite doing it adversarial way. They're using what's called anomaly detection, which is basically identifying in a stream of data something that looks unusual. But it has the same feature you're describing, which is now the NSA analysts don't have to type in a specific query, but they can just say, tell me about something that looks unusual.
Absolutely. It's just not feasible anymore.
So let's talk a little bit about the gaps, right? Where do you guys see the gaps in machine learning and some of the implications around that?
So one of the things that we were just talking about now is moving these traditional algorithms from batch to stream-oriented.
Yeah.
So the traditional algorithms say, you give me a set of data, input-output pairs, and then I learn a model, And now you make a query for that, give me a new input, and I'll predict the best output. And they were all written assuming that the data was a finite resource that you were given once. But that's not really true anymore. So now it's data is coming in a continual stream, and you've got to update the model over time, and you've got to decide how much do I trust what I learned yesterday versus how much do I trust what's happening today, and is it different? And should I then forget what I knew before? Should I remember it because next year at this time may be the same as last year at this time? So all these models have now been rebuilt in a stream-oriented fashion.
And is there a concept of like layered learning, right? Certain kinds of learning stay the same, and then there's other kinds of learning, data being in continuous motion. Very, very interesting thought around that.
I think my view of the gaps right now is largely about talent.
Yeah. We touched upon this a little bit, but I'm really excited to hear your thoughts on that.
Well, we've measured the performance of our 100,000 users as they enter predictive modeling competitions to see who's the best at making accurate predictions. And so, and I know most of the guys at the top of that community, the top 10 do stuff that the top 100 can't dream of. The top 100 do stuff the top 1,000 can't dream of. And the top 1,000 do stuff 100 times faster than the top 10,000 can. Like, there's this massive curve of capability and speed. And there's very little at the moment around kind of how do we train the next generation of those top 10s? How do we identify them? I was telling Peter actually beforehand that of our competitions, nearly all of our winners from the past year actually learned about machine learning by watching Andrew Ng's YouTube lectures and Coursera course lectures. Like, literally the best place to be trained right now is through online courses. So it's not clear to me how kind of this talent gap is going to be filled and how we're going to build and identify the brilliant data scientists.
So yeah, go ahead.
I take a slightly different approach. I think it's possible to augment that talent gap with software to a very large degree. And if it's the case that the top 10 people are consistently winning in the competitions, then it must be the case that they don't reinvent the wheel for every competition. They must have built parts that they reuse for across these different competitions. So that basically says it is possible to build software that will do a good bit of heavy lifting for you, that you don't really have to reinvent it over and over again. I think the other point is, one of the biggest gaps in industry, and as Jeremy pointed out earlier, is sort of to do with culture, right? Either you're going to trust data and make decisions, or you're going to be obsolete. You just have to pick one, and it's.
So I guess I would agree with that. There's this notion of the hippo, the highest paid person's opinion, where everybody gets into a meeting and presents their point of view, and then the guy that's paid the most gets to make the final call. And you want to decide, is that the type of organization you are, or are you one that's driven by what does the data say is the right thing to do? And so I think going along with that is this notion of openness, that in a lot of companies, everyone has been trained to say, well, it's my data, and I have to keep it so that my division will keep performing better than everybody else's division. And now you have to change that to this notion of this data has some value to you, but it also has value to everybody else in the company.
Especially now that, the government, for example, has opened up 150,000 data sets. Like, your competitors have access to all this open data.
Yeah.
You've got to at least be sharing stuff internally.
And I think the final piece is just embracing this notion of uncertainty, to say that there is no one right answer. It's not that your programmers are going to write something that's absolutely correct. It's that you can make predictions, and some of them are going to be wrong. We've all seen these spreadsheets of quarterly growth and so on, and they all have precise numbers, and they always go up and to the right, and they're always wrong. So why do we keep doing that? Why can't we do something that says, well, here's a prediction, but this is a range, and here are some possible other predictions, and here's the low one, here's the high one, here's the black swan that's a 1 in 1,000 event, but if it does happen, it's really, really important. And so we've got to consider that as well as just considering that single point prediction.
It's funny that hasn't taken off more. Back 20 years ago, I remember we were using an Excel add-ins like Crystal Ball and At Risk, and everybody was expected to do a stochastic analysis of a model. But
yeah.
If anything, it's disappeared rather than taken off, which is surprising.
So quantum computers are here. Qubit is changing a lot of things. I want you to leave the audience with one key takeaway as a big opportunity.
I think the big technology opportunity is taking advantage of ensembles of decision trees and deep learning networks in a very particular way, which is that these things let you throw as much data at them as you like, and they'll basically never overfit, and they'll be able to find all the richness that's there. So to use these effectively requires a very high degree of creativity to think of all the things that you can throw at it, and you've got to get out of that mindset of filtering, which is, oh, that won't work, that won't work. And that's the approach that our top data scientists all use.
I guess I'm skeptical of quantum computing, and it'd be great if it works out, but it's not here today. And I think there's just so much that you can do today with the data and the computing power that you have that focus on that, and then as new technologies come in, use them when they're really available.
So from my point of view, I think I just want to reinforce that we should trust in Moore's law. Computers are going to get cheaper and faster, and we should let them do more. We should not leave the onus of coming up with all the ideas only on people. With technologies that we have access to today, the computers can do a fair bit more than simply process our queries.
Great, excellent. I know the audience has a lot of questions, so we will open it up for questions.
So there was a lot of talk and discussion about sort of filling the talent gap in regards to data scientists in the community currently. What do you think would be sort of this? I guess this is kind of directed at Jeremy Howard. In a previous talk, you kind of mentioned that some of the core tenets to a good data scientist are solid background in machine learning, solid background in coding, and sort of the creativity and tenacity to bring it all together. What do you think about a team-building approach in which you can kind of leverage those specialties into individual people that are specialists in that area, and how would you sort of find a way to allow them to communicate in such a way in which they're all on the same page and functioning almost as if they were close to one individual?
Sure. So for those who haven't seen one of my talks about talent, what he's referring to is we analyzed our top talent to find out the common characteristics of them, and we found that there were 4 in particular, which was tenacity, creativity, curiosity, and skills in coding and math. Now, clearly, you can't take one person with each of those 4 things and put them together and expect them to be that person. What you can do is you can bring together a domain expert and a great data scientist and expect them to do great things together. The domain expert's role is to come to the conversation with a deep understanding of 2 things. What are the specific actions that this organization can actually change? We could change price, we could change where we put our next store, we could change the color of product. And what are the strategically important things of this company, right? So, basically what drives profit. They then come to that conversation with the data scientist, and the data scientist says, whether it be, with using software like Ayasdi to identify, interesting patterns, or using a supervised approach like deep learning to identify drivers of an outcome, the conversation basically is, okay, I'm trying to achieve this, and these are the things, the levers that I get to pull to change it. And the data scientist says, okay, a data-driven approach would look like this. Do you have that data? So, you really combine the software and the domain expert and the data scientist together in that kind of conversation.
There's a couple of questions here.
In the next 3 to 5 years, you talked about democratization of the computation for machine learning. Maybe Peter can also answer it. In the next 3 to 5 years, you think that Ayasdi will have its service available in the cloud, or will it always be
So we
it's
already
like a machine learning as a service?
So we already have a cloud-based service available. Roughly half our customers today use our cloud-based service. And frankly, the other half don't use it because of legal constraints. Right? They would love to do it, except their data is sensitive, or it can't walk off their premises, or if it might be personally identifiable or something of that sort. It's interesting that there are some enterprises who are sort of much more competent with IT resources and such, and others who are not. From my perspective, what really matters is sort of the end business users, right? It's their problem that they need to get solved. And if it's the case that you're in an organization where IT is supportive and you have legal constraints on your data, then it should be an in-house solution. And if it's the case that your IT department is maybe not as advanced, or if there are legal constraints on your data, then you should go with a cloud-based model. From our perspective, it's we are happy to work with in either situation, but clearly operating in the cloud environment gives you a multi-tenant system in which you sort of economies of scale help you.
But the real problem is that as the data comes in, the machine learning as a service creates a model of the data. Now, what if the model changes? That's a
Right. So it depends on you can recreate the model every so often, right? You don't have to rely on the same model for eternity, and you shouldn't anyway.
Well, there's actually, and like beyond further than that, there are algorithms which are specifically designed to understand the time component of data and adapt their parameters over time. Yeah. But the other thing I'd say is it's surprising how little that happens. Like models describe kind of a connection between inputs and outputs in terms of causality. That's what they do behind the scenes. And my experience is that once you've built a model, the input parameters change a lot, but the underlying way in which they combine to create outcomes, other than in adversarial situations, doesn't change that often.
Right, but there are situations in which you have the case that new data arrives, yes, and your model is not fit for that anymore.
Yeah. And if your model has temporal or spatial components,
absolutely,
suddenly added to the data, then your data is going to change. Okay? Okay, next question.
So actually, follow up on that question is, one of the problems of taking this kind of brute force approach in machine learning from raw empiricism is that you're really looking at correlations, and you don't really get a lot of insight into causality, and you don't know that until the correlations stop being true and your model breaks, right, and you can't predict when it's going to break. And in science, we solve that by developing theories and abstractions.
Right.
What can machine learning do to help us get towards the theorization and theory generation? Do you think that's impossible, or are we making some progress in that level of abstraction?
Right. Okay, so there are a few ways to talk about that problem. The first way to think about it is that there are cases in which causality is built into the data, right? So a very good example of this is in pharmaceutical situations, right? If you're talking about drug discovery and so on, you usually have data about DNA, you usually have data about gene expression and so on. And we know from science that your changes in your genetics will lead to changes in gene expression. So there is causality built into that situation, so you can exploit that. And there are many situations in which causality is not built into the data. And then look, eventually, if you're going to make decisions based on data, you only have correlations to rely on. You can't really do much else.
Unless you build reasoning, if you build some sort of reasoning.
So reasoning is a very funny concept, right? I mean, it
works.
Basis. Yeah, it works for some situations. If you have a bunch of text, if you can read a bunch of books, and if there is text available about the problem, then yes, you can reason. But if you don't have any prior knowledge about it, then yeah.
So I think you can't discover causality unless you're allowed to do experiments, right? So if you're just observing the world, you don't know. But if you can do an intervention, then you can discover that.
Right, and this is why one of the biggest, to me, problem phrases of the last few years is data exhaust. Data exhaust means you only use the data that you already have, which means by definition you're not doing the experiments to identify causality.
Yeah. So in the theory of active learning, you figure out what's the next piece of data that I need, and then you go out and collect it. And there certainly are formalisms that are designed to represent causality. So the Bayes nets and Udea's pearls work for the last few years has really been concentrating on causality and how to represent it.
Yeah, and we can measure the effectiveness of those algorithms. So for example, on Kaggle right now, there's a competition called cause-effect pairs, where thousands and thousands of interrelated variables where we know the causality have been inserted and people have to reverse engineer them. And at the end of that competition, we're going to have exact measurements of the effectiveness of each algorithm for identifying causality. So this, this is a well-understood area. It's not something we don't know about.
Next question.
What are the areas where you shouldn't trust machine learning? For instance, we know that in finance, I mean, the people in finance have been the early adopters of machine learning, building models and testing them out. And we can make an argument that probably wasn't a good thing. What are the areas where you wouldn't trust machine learning?
Well, arguably, they've been extremely successful at using machine learning. Right? It's the case that people got greedy and did some wrong things, right? We basically packaged up things into sort of securities that weren't sort of as they shouldn't have done that, and they knew they were not in the right there. But as it concerns machine learning, I think it's been extremely successful in finance. They've generated a lot of return that they would not have ordinarily been able to do.
Yeah, so I think there it's more a question of mechanism design than machine learning, right? So there was this idea of optimization, and given the mechanisms that we had, people tried to optimize them, whether they used machine learning or whether they used their own intuition or what. I think that was immaterial. What was important was the mechanisms we had were such that they could get us into this state which was unstable.
Right.
And if you're clever about setting the rules and having governors, you could say, well, trades can only be made at a certain velocity, and you have other ways of sort of damping down these wild swings, then you'd be in a better position.
I think it's difficult for a lot of folks to kind of select a machine learning vendor or technology or whatever, because frankly there are a lot of snake oil salesmen in the industry right now, and like I would be terrified of betting my business on a piece of machine learning technology which I either didn't understand or didn't have a really rigorous way to test the effectiveness of, because if you think of it as just this black box which is going to do magic, then you've got the ability to destroy your business using black magic that you don't understand. So that's where I would be super careful of machine learning.
And I think Peter and I was having a conversation about this. You have to establish baseline. You have to understand precision and loss and how much is the variance, all of these things before you go deep into it.
And these kind of valves that Peter was describing around, frequency and size, and make sure those things are in place.
Question?
A lot of the work in corporations is focused on human relationships, which are sort of by definition ever-changing and never well-defined, and influenced by many factors that are not in the data. So the use of machine learning for marketing has a relatively low risk, but to find those core patterns that kind of describe all human relationships, is that some work that's being done?
Absolutely. I mean, in fact, we were just talking about this beforehand, that the exact area that the more sophisticated machine learning algorithms work best is where the underlying rules that govern the systems are things that we don't have a strong intuition for. So something like understanding how human behavior changes is complex, and it's exactly the kind of thing that if you just provide the inputs and the outputs, modern machine learning methods are particularly good at finding the incredible complexity of underlying kind of causations and systems going on inside. So that's why actually machine learning for marketing is perhaps the hottest area, like investment in everything from kind of online advertising marketplaces to churn models to so forth, is actually an area where machine learning's been very, very successful.
Dan Ariely has this example of You give people a choice of which article of clothing do you like the best, and you show them 3. And he says one of the most predictive variables is the one on the right. But nobody says I chose the one on the right because it was the one on the right. They say, well, I like the color, I like the texture, and so on.
But an algorithm will find that just nice.
Yeah, the algorithm picks that out really fast.
Okay, next question.
Yeah, so kind of elaborating on that topic, I wanted to know what kind of problems do you think machine learning, is kind of beyond the realm currently of machine learning?
What's beyond
Beyond
Google?
the
That's
realm.
probably the
I can
best
tell
place
you
to
one,
tell us.
natural language, just fluent natural language. If you look at reviews and blogs and things like that, where people speak in grammar that is not very structured, it's very difficult for machine to learn that because you don't understand the words. Like, for example, birds fly. Does penguin fly? Because penguin is a bird. We know these things inherently, but the machines don't. So there you have to learn context, you have to learn grammar, lots of things behind the scenes, and then you have to bring in machine learning and NLP together. Those are hard.
But it's amazing what we can do in that
Yes,
area. I mean,
yes,
we
absolutely.
ran a project last year where we took 30,000 handwritten school essays, all of which had been graded by 2 teachers, and tried to find out if anybody could come up with an algorithm that would grade them the same way the teachers did. The best algorithm was more consistent with the teachers than the teachers were with each other. So we already have algorithms that can read students' essays with all of that complexity and rate how good an essay they are more consistently than teachers can.
So I think another example of that would be the machine translation,
Right.
where it used to be that you built those systems by hiring teams of linguists and having them write all these rules. Now we do it just by gathering examples. Here's a document in English, here's one in French, use that as an example, align the pieces of the English to the French, and now you've got a model. And that works great, and in many places it works as well as a human translator. It's not quite there yet. But the places where it falls down is where you don't have examples, where you haven't seen this text before, and mostly where it interacts with the real world. Right? So if I give you a sentence like, I dropped the brick on the glass table, it broke, we know that it refers to glass table, and if I now have to translate into a language where table is masculine and brick is feminine, I can make the right choice. But that's a fact about physics. It's not a fact about language. And getting all those types of facts about how the world works integrated into the language, I think that's where we're going to have trouble.
Right. I mean, there's some specific areas. Sorry, Ajay, go on.
Sorry, I said eventually I think we are going to get to those as well.
Yes.
Right
Yeah.
there, with computation and data, we will reach there.
But you can kind of find these places that machine learning is not good enough when you look for places where we're currently using humans for things, right? So like an example I really like is protein folding. We don't have algorithms that do a good job of protein folding. So a group of researchers built a computer game which basically visualized the folding of proteins and told people that they can fold them by hand and win points. And that's resulted in 7 peer-reviewed papers of new proteins that have been folded because humans are better at that than computers. But pertinent to
Actually, I take a different view on that. There was that one successful story about that, and that's great. But isn't it the case that you distributed the computation? That you said instead of the number of human beings attempting to solve that problem and the amount of time they spent on it was sort of vastly.
I think it's taking advantage of something humans are really good at, which is we actually have far more connections in our brain than the Google brain, and it's really great at seeing stuff. But on the other hand, the result of that is now they've fed back that to the algorithm researchers, and the algorithms are improving.
Right.
But generally speaking, stuff where our brains are fine-tuned at recognizing spaces and images, we're still better than that than computers are for now.
Yeah, we'll get there.
And our brains are good at 2- and 3-dimensional data, but if it was 4-dimensional, we can't do it anymore.
Exactly.
Yeah, so if you're going to invent a time machine, maybe bet on a computer.
Question?
Hi, I guess this is a question mostly for Peter. One way to think of Google is as a machine learning company. It is learning each of us to be able to deliver things to us more easily and effectively. Can you share with us a little bit your view of your predictions about where the conceptual model for modeling us is going, how integrated it will be, how sophisticated it will be, and how do you guys think about that internally over the next sort of handful of years?
Yeah. I guess the first thing to say is that there's two parts of it. There's each of us and all of us. And I think more of it is in the all of us, in that I don't really want a model of you. I want a model of everybody and everything, something that everybody knows. And I think this varies among companies. So Amazon really wants a model of you. They want to know, what did you buy last time, so that they can sell you something like that the next time, because you're going to be pretty consistent in your buying habits. Google wants more a model of everybody rather than a model of you, because most of the time when you come to Google, it's not because of something you already know, it's because of something you don't know. And so you're pushing beyond your boundary to a place where we don't know anything about you. And so it's better to go on what we know about everybody rather than what we know about you. And so we're trying to build both of those, to have a better model of what each individual is, but also of combining everybody's knowledge together. And that goes for the words you use, the paths you take. When you type something to Google that isn't quite right, we say, did you mean, we give a suggestion, and we're able to do that not because we know about you, but because we know about other people. That in the past, somebody typed this thing first, it didn't work, then they typed another thing. Now, when you type the first thing, we'll take you directly to the path that they eventually ended up at.
One more question?
So it kind of brings up a question of trust and risk. I'm just thinking about trust and risk. So in the case of Google, and correct me if I'm wrong, but you're supplying information and people trust that they make their own decision about what to do with it. But in the case of a machine learning algorithm that invests your retirement fund or chooses a mate or something that's very high risk, the decision-making side is still machine-based. How do you develop trust in those kinds of things where the experiment is not possible?
So I guess I had that kind of situation at my last startup, which was doing insurance pricing, and insurance pricing is the most important decision for an insurance company to make. And we wanted to get to a point where algorithms would price insurance, but we had to build trust. I think this is where you have to basically draw nice pictures. You need to basically show what the model's saying in a way that humans can understand it. And then there's three phases. The first phase is show the humans the pictures and let the humans use their expert judgment to decide what to do, supported by that kind of predictive modeling and visualization. The second step is to give the computers some limited ability to make their own changes in situations in which they're very, very confident. It's a very, very well understood area, and it would be something that's kind of time sensitive. And then the third step would be, on the trust that you've built up through those stages, would be to slowly decrease the number of kind of valves that Peter's describing, where you start to give it more ability to change things and you start removing the constraints.
I think it's also the case that in most situations, eventually there's a human being in the loop, right? If an algorithm chooses your mate, it doesn't really put you in bed with people, right? It's your call at the end of the day. And similarly, if you're making an investment decision, there are suggestions certainly, but it's the case that you have to make your own decision. And to the extent that we can make a user's life easier in making the decisions, exactly by using visualizations, to Jeremy's point, then that's sort of the way to go.
You can't really protect yourself from a malicious. Sorry, last question. You can't really protect yourself from a malicious data scientist when there are only a few thousand of them around.
There are no malicious data scientists. We're all lovely people.
Yeah.
That's it for the questions. We'll be around, and you can ask us individually.
Great. I'd like to thank our speakers for sharing your perspectives and opinions so candidly. We really appreciate that. And Janet, for your expertise in leading the discussion. As a small token of our appreciation, we have for you a Churchill Club speaker t-shirt, much coveted. Please wear it in good health. This program will be available on the Churchill Club YouTube channel within a day or two, and you can also look for it on the C-SPAN website. Accenture's offered to cover our parking, so ask about that on the way out.
Thank you.
And you have been a wonderful audience. Thank you so much, and we'll see you soon.